Cam.
Classic optics is when we speak of lenses, mirrors, and prisms. Integrated optics is when we do the same things with planar waveguides, or nowadays more with nano waveguides. And we talk about integrated photonics when we integrate more functions, such as modulation or detection. And it gets really exciting when we integrate this together with electronics. So when photonics and electronics are merged, so there's a seamless transition between digital, analog, and photonics. This allows us to build photonic electronic systems on chip that are more complex than anything we have seen so far. Optical communication is needed very much nowadays because we see a bandwidth explosion. The bandwidth explosion is related to quite several factors. There's Moore's law, there's an increase of the number of users, there's more broadband access, and there is more services. So this really leads to this bandwidth explosion. And that can only be handled by optical communications. So specifically, when we look at how this is done, what we need is transceivers. And the older among us, they remember that transceivers used to be bulky. They used to be gold boxes, expensive, and energy hungry. What we need now is really lean, energy efficient, and good value for money solutions. And these solutions, they are provided by photonic integrated circuits or by electronic photonic integrated circuits. They can provide these solutions. Silicon technology really excels at reducing costs, and that is done by scaling. No other technology can provide 10 billion transistors on a single chip for a few dollars. So if you think of transceivers as ICs, you really see where the value is. In addition, silicon technology also provides a value chain that allows to hop on and exploit what other people are using in electronics industry. So there is like a ready technology and value chain that we can profit from if we do integrated photonics on silicon. EPIC stands for Electronic Photonic Integrated Circuit. It means that we have combined a photonic integrated circuit, so a circuit that combines photonic building blocks such as waveguides, fast photodetectors, and fast phase shifters and modulators, with integrated electronics, that is CMOS transistors, and in some cases, like in ours, bipolar transistors. And all this combined on a single chip is what we call an EPIC. A silicon photonic transceiver has at its core an photonic integrated circuit or an electronic photonic integrated circuit. And that IC is fabricated in a silicon foundry. And in the silicon foundry, there is where all the silicon technology runs to make such an integrated circuit. So if we start, we typically have to design the IC. There's a intense co-design of photonics and electronics to optimize the IC. This will give us the layout of the IC that we then send to the mask shops who returns the masks to us. And with the masks, we produce the IC in the foundry, so in the clean room, where the processes run, such as lithography, implantation, and so on, that are combined to make photonic building blocks, such as detectors and waveguides and modulators. And on the other side, we also make in that process the transistors, such as CMOS transistors or bipolars. And everything is combined under a common backend that basically provides the electric connectivity that we need on the chip, so the wiring that connects the different building blocks. And then the wafer leaves the foundry. The wafer is being tested thoroughly. And after that, we dice the wafer. So as we single out the electronic-photonic integrated circuits. And that is what then goes to the packaging. And so we have to connect the fibers, the ICs need to connect it to the PCB, so the board around. And that has to be housed, be packaged. And that is what we call the transceiver. Now let me look into the crystal ball. I think the what will happen is that we will see the integration of novel materials. It's very similar to what has happened in microelectronics. Microelectronics classically used to just process silicon, but in recent decades there have materials been added that were unthinkable like 30, 40 years ago, such, for instance, as copper or high-K dielectrics. So these materials, they were very uncommon in silicon processing, but they are common nowadays. And I think something similar will happen also in silicon photonics. So we will see the integration of III-Vs, certainly for the integration of the laser sources. This is a very, very interesting way of integration, because sources are a major cost factor, and having that integrated in a planar process would provide us with huge cost saving advantage. But I also think other materials are very interesting, such as ferroelectric materials that could provide us with modulation capabilities that are not reachable, or not in reach with conventional silicon technology. So I think there's, in terms of development, a lot to do in terms of new materials. And we also need to look at the technology readiness that makes these materials available to external users, so that they can use the silicon technology as if there were no new materials.
TechCam.